Should I start?
Hi.
Yeah, you can go.
Okay, I can go. So I'm very happy to introduce today's speaker, Brendan Casey. Brendan is a scientist, a senior scientist at the Fermi National Accelerator Laboratory, the Fermilab in Illinois, in the US. He has worked from 2002 to 2011 in Dzero experiment at the Tevatron. And since 2007, he has been involved in the g-2 experiment at Fermilab. Brendan has received in 2007 the Wilson Fellowship from Fermilab. In 2012, the Early Career Award from the US Department of Energy's Office of Science in support of his involvement with the g-2 experiment. And in 2018, he received the Exceptional Performance Recognition Award, reward for overall leadership of the Muon g-2 experiment transition to operations, and for leadership of the g-2 tracker design and construction. So Brendan is going to talk to us today about the first results of his very nice and very difficult experiment, the Muon g-2. So I'd like to ask you all to turn on your microphone so we can welcome him. Hi. Okay.
Welcome.
Yeah. Welcome.
Welcome.
Thank you, Brendan.
Okay, so I start sharing my screen.
Yeah.
Okay, and as we just said, I'm going to talk about the first results from the experiment. I'm very happy to give this and very happy for the invitation. Okay, so what we're talking about doing is measuring particle properties here. And the reason we do that is because elementary particles can effectively talk to each other through loops and boxes. And this allows us to learn information about new particles by making precision measurements of the properties of old particles. And there's two kind of classic examples of this. The first is BB bar mixing, where we could look at a bottom meson converting into an anti-bottom meson, and looking at this one parameter, measuring the mass difference between the heavy and light eigenstates, it can tell us that the top quark mass is much, much heavier than the W boson mass. And this was the first hint we got that that was the case. And it also, you can see the B meson is about 5 GeV, and the W boson is 80 GeV. The top is much, much heavier. So there's these particles that are much, much heavier than the B meson, but we're learning all these things about them just by measuring different properties of the B meson. So another example is the relationship between the top quark mass, the W boson mass, and the Higgs boson. So if we make a very precise measurement of the W boson mass, and we make a very precise measurement of the top quark mass, it can tell us where the Higgs boson should be if it's a standard model Higgs. And we see here, this is a 90% confidence level band, and here's the measured value of the Higgs mass. So within the 90% confidence limit, we could see that the Higgs mass is where we think it should be. And this is one of the main things that tells us that the Higgs boson is a standard model Higgs boson. So the one property I'm going to talk about today is the G factor. And the G factor relates a particle's magnetic moment to its intrinsic spin in units of the Bohr magneton here. And we can ask what this is for a simple classical system. If we look about a rotating charge, we could easily calculate the magnetic moment, and we can calculate the angular momentum. And when we look at the ratio of these two things, it's almost always coming out to be charge over twice the mass. So this is essentially the charge to mass ratio with a factor of 2. And for this system here, what we see is that the G factor is 1. And it's something that's true in classical systems and also in non-relativistic quantum mechanics predictions, we always come out with the prediction that G equals 1. So we could look at what the G factor is predicted for the muon. And the first term we get is 2 instead of 1. We get 2.00. And this comes from Dirac. It falls out of Dirac's equation. If you solve Dirac's equation in a weak magnetic field, you see you always wind up with an extra factor of 2 associated with the spin of the electron. And this factor of 2 comes from the extra degrees of freedom that are associated with antimatter. So since this is a 4-component spinner instead of a 2-component spinner, you're getting these extra factors of 2. And that's really what's telling you that in relativistic quantum mechanics, the prediction is 2. Now we could look at the next terms, which are 2, 3, 3, 1, which come from quantum electrodynamics. And the first main term here is the Schwinger term of alpha over 2 pi, where Schwinger was, this is one of the first calculations in quantum field theory, showing that renormalization works and showing that Schwinger could calculate this self-energy diagram for the electron at that time, but it's the same for the muon. It's now calculated out to 10th order by Kinoshita and his collaborators. And you can see this is just a fraction of the 10th order diagrams here. The next terms are the ones dominated by quantum chromodynamics. So that's 8.3. And these come from data. So these are all measured from data. I'll talk about that a little bit more. Either E plus E minus R-scan experiments or E plus E minus factories that are doing radiative return. And what you see here is the main thing is E plus E minus goes to pi plus pi minus. G minus 2 is essentially the integral over here, but there are also higher order corrections. And I'll talk about those more in a few slides. The next terms are the electroweak contributions, 622. And those were most recently measured or most recently calculated and updated after the Higgs boson mass was known out to second order. And these are just a few of the diagrams here for that. So our predicted value is 2.00233183,622. We can compare that to the measured value of 2.00233184,182. Okay, so we're starting to see agreement in the QCD terms, and effectively, once we get in the electroweak region, there's not very good agreement at all. So the measured value comes from the Brookhaven EA21 collaboration, at least the measured value up to about a month ago. And this is a culmination of large improvements over 4 decades of experiments that started out at Columbia and Liverpool and then moved to CERN, 3 generations of experiments at CERN. They moved to Brookhaven, and this led to this best measurement up to about a month ago. So if we want to understand this discrepancy now, we could take a closer look at it. The measured minus predicted value of G minus 2 over 2 differs by about 28 times 10 to the minus 10. And with the errors, our best understanding of the errors, that's about a 3.8 sigma discrepancy. So we could take a closer look at that. If we think about just the electroweak contribution to G minus 2, the electroweak contribution is about 15. Okay? So the discrepancy that we're seeing is almost twice as large as the electroweak contribution. So if you want to describe this with some sort of new physics, you automatically think that this should be something that's big, right? Because its contribution is twice as large as the electroweak coupling. So it's either massive particles around the electroweak scale with larger couplings or slightly larger with larger couplings, but it's big. It's something that's big. Now, this is the mystery that we have. If this is something that's bigger than the weak force, why didn't we see new particles at UA1, UA2, LEP, LEP2, SLD, the Tevatron, or even now the LHC, right? There have been many chances we've had at new energy frontiers to discover new particles that would be the size of the electroweak force or even greater than the electroweak force, and we just haven't found them. And there's 2 examples here from the LHC looking at standard model cross sections for different processes from PP bar to PP bar, or sorry, PP to PP, going all the way down to triple Gauge boson productions. And you see very good agreement between the standard model prediction and the data measurement. So there's nothing jumping out in the standard model. And we could also make direct searches or targeted searches. So this is a search for supersymmetric partners to muons. And again, we're not seeing anything here. And the particle masses here are well above the weak scale. And the couplings that we're looking at are much larger than the electroweak coupling. So there's really nothing popping out here. And that's the first big mystery that we have with this discrepancy. So we go back to this discrepancy and take a second look. The next thing we see is that this really starts to pop out in the digits that are dominated by QCD. And so maybe this is simply an underestimate of the QCD contribution. And I say simply in quotes because it's a fairly sophisticated estimation and it's really data driven. But and it's a lot of work goes into it. But a lot of people look at the discrepancy and say, okay, if it's showing up in the QCD digits, it's probably that we've underestimated the QCD contribution. And we've all seen anomalies that wound up being underestimates of QCD effects. So, none of us would be surprised if this turned out to be an issue with the QCD part of the calculation. So a good thing about that is that there's been a group of theorists called the Muon G-2 Theory Initiative. And this is a group of 132 theorists and experimentalists that have mainly been working on this for their entire careers. But they got together as a group of people between 2017 and 2020. And in a series of workshops, they really put together a major update of the predicted value of G-2. And they produced a 196-page white paper with 824 references. So it's a very comprehensive look at all the inputs that go into the predicted value, what's consistent, treating everything on consistent footing, and coming up with a new prediction. So we'll look at that for just the leading order hadronic vacuum polarization. And what this comes from is it's the self-energy term where you have the muon talking to itself with a photon, but now the photon polarizes the vacuum and it polarizes it in such a way that you get a hadronic loop of quarks, gluons, and resonances. So that can't, it's hard to calculate that with pencil and paper. But we can calculate, we can get a handle on this from data. So this can be taken directly from data by the measurement of the differential cross-section of E plus E minus goes to hadrons. So if you assume analyticity and the optical theorem, you can cut this diagram in half right here, cut through the bubble, and then can change this muon into electron. And this bubble then is a bunch of hadrons. And you could see how this is simply the process E plus E minus goes to hadrons. So there's two ways that we can handle where we can get this from data. The first is R-scan data, where you vary the beam energy of the electron and the positron, and you sweep through from low energy to high energy, and you count how many hadrons are coming out along the way. The other way, which gives us a lot more data, is to get data from flavor factories, which are sitting on a resonance. So such as the upsilon resonance or a psi resonance or a phi resonance. And in this case, there's some fraction of the time, either the electron or positron will radiate a photon before the collision. So the center of mass energy of this collision is below the energy of the resonance. And by doing that, and then looking at the invariant mass of the hadrons that come out, you can access this entire energy region, even if you're sitting at just one energy with your machine. And this E plus E minus to hadrons data is kind of considered the gold standard by the community and by the Muon G-2 Theory Initiative. And that's the main thing we're using to get to the QCD input for G-2. Now, the other interesting thing about this, or the other feature of this, is there's a 1/s scaling in the kernel. So this is your cross section that you're measuring here. This is a kernel function, but then you've got this 1/s scaling. So that pushes this all. It really weights the E plus E minus to pi plus pi minus in the rho and omega region. Okay, so that's really where we have to focus. And if we understand that region, that pretty much tells us everything we need to know about it. So we could focus on that region here. What's plotted here is the invariant mass of the pi plus pi minus system in E plus E minus goes to pi plus pi minus data. And this is the cross section as the function of the invariant mass. And what you see here, this rise is the rho. So this would be the rho peak here. But then you have this sharp shoulder here, which is a feature caused by rho and omega interference. So we have a lot of data here. And the two most sensitive values on here are the Babar data, which are these black points here, and the Chloe data, which are these red points here. And you could see by eye, they don't really agree. Right, and especially when you integrate these two distributions, especially in this region here, because they don't agree, the integral is not going to agree, and they're not going to do a very good job at predicting, or they're going to disagree in their prediction for muon g-2. And that's what you see here. This is the Chloe prediction for what the hadronic contribution of g-2 should be. This is the Babar contribution. This is BESS3, which is sitting at the psi resonance. Clio C also sitting at the psi resonances. And then this is SND and CMD. These are R-scan experiments at Novosibirsk. And this is old data from them. One of the interesting things, we're expecting major updates from these experiments. Now, if you put this all together, this is the combined value that comes from the g-2 theory initiative. And if you look at it, Chloe has the smallest errors. So Chloe kind of pulls the central value towards it. But this discrepancy between Babar and Chloe kind of makes you expand it so that the combined value isn't getting smaller than the Chloe errors. The combined value is getting larger than the Chloe errors. But that's where that sits right now. Now that's the main channel. The E plus E minus goes to pi plus pi minus, but we have to do all the channels, right? This is E plus E minus goes to hadrons. So we have that now, mostly almost entirely data driven. And just an example, here's the 2-body decay here, but here's a 3-body decay, E plus E minus gamma from Belle. Here's a 4-body decay, pi plus pi minus, pi plus pi minus. And here's even an 8-body decay, pi plus pi minus, pi 0. And then eta again going to pi plus pi minus pi 0, and the 2 pi zeros going to 2 photons. So we have the table of everything we have to put in here. As I said, it's almost all data driven now. You know, there's only a few channels like this KK pi. You know, there's a measurement of K short pi, and then you assume that that's the same as K long pi. Right, so there's a few channels that aren't really measured, but almost everything now is entirely data driven. So, you know, we know this very well now. Now, there's other ways to calculate this, and one of the most promising ways is using the lattice. So it's a hard lattice calculation, so it's ambitious, but what you're trying to do is look at the QCD input to g-2 and calculate it from first principles by integrating over discrete lattice spacing and then extrapolating to a continuum limit. And when we look at that, here are the results from multiple groups. And you could see right now with most of the groups, it's not really competitive with the E plus E minus. This is the E plus E minus and different combinations of E plus E minus down here. And actually, pretty soon after the first version of the white paper came out, the BMW group updated their results and put out the first lattice result that is approaching, you know, it's competitive now with the different E plus E minus comparisons. So this is a very, very big milestone for the community, because people have been working for a long time to get Lattice to the point where it's competitive to E plus E minus. So this is a huge milestone for the community. And what we mainly want to see is the other groups start to update their results and see if they agree with the BMW results. Because if the Lattice comes in over here and the E plus E minus comes in over here, then, you know, it's going to be a clear indication that the QCD contribution is not in control, right? It'll give us another, we'll have to answer a different question, which is, why does Lattice not agree with the E plus E minus? But it will tell us that, you know, the hadronic contribution is not under control. Okay, so if we look at this discrepancy now, we go back to that. We have our predicted value, and we have a ton of work done by a ton of people that have updated both the QCD contribution and all other standard model contributions. So we have QED, electroweak, hadronic vacuum polarization, leading order, and next to leading order, and next to leading order, hadronic light by light, which I didn't talk about at first order, and leading order, next to leading order. And we have an updated value from the G-2 theory initiative, which differs by 2 in this last digit. And the error went from 84 here to 86 here, okay? So it's essentially unchanged after all this work by these hundreds of theorists, but it's confirmation that the numbers was on good footing before. So we do expect another major update of this once the new R-scan data comes out from Novosibirsk, which hopefully will happen soon. And we expect more data from the flavor factories, from Belle 2 and from Best 3. And Babar has a lot more data on tape they haven't looked at yet. And we expect to have a major update when the BMW Lattice result is confirmed. But for now, this mystery remains. We have not been able to solve the mystery by demonstrating there's some problem with the QCD contribution. So the only thing left to do is look at the measured value, right? There's no reason to say that there's not a problem with that. And so we should redo this measurement. So our technique of measuring G-2 brings us down to measuring 2 frequencies, the muon procession frequency and the proton procession frequency. And then we have other inputs which relate the muon and the proton spins. So what we have to do is we get this muon and proton procession frequency by putting both muons and protons in the same magnetic field and watching how fast they process. So muons, we do that by counting the number of high energy positrons versus time from a stored muon beam. For protons, we do this with the free induction decay in nuclear magnetic resonance probes that we have in our ring. And then these external probes, which are essentially giving us mainly the ratios of masses between the muon and the proton, we look at the difference between hyperfine splitting, where you have a hydrogen atom, where it's an electron rotating around a proton, and a muonium atom, where you have an electron rotating around a muon. And looking at the hyperfine splitting in these two systems allows us to give us a handle on everything else we need to know to convert G-2/2 into the ratio of a muon spin to a proton spin frequency. So we do this in a storage ring, and the main observables that we have is the difference between the muon procession frequency and the cyclotron frequency. So the cyclotron frequency is the charge to mass ratio times the B field. The spin procession frequency has G/2 coming in, but again with Q/M/B. So if you look at the difference frequencies between these two, then you get G-2/2 directly coming out. So that's why this difference frequency here is the main thing we want to look at. And this was developed and improved by the CERN 1, 2, and 3 experiments and the Brookhaven EA21 experiment. So the CERN 3 experiment did this with a storage ring that looks very similar to the storage ring that we're using. The main difference is that they have 40 magnets here that built up their storage ring. And you know, we have to extract G-2, we need to understand what the magnetic field is seen by the muons. And for a system like this, no matter how well you understand the magnetic field within the magnets, you're going to very quickly get to a point where your error is dominated by your uncertainty in the fringe field. And fringe fields they're hard to measure, they're hard to model, there's all sorts of different things there. So that was really one of the limiting factors at Brookhaven, was just that, you know, dealing with the fringe fields between all these different magnets here. So one of the big advantages of Brookhaven was to make one continuous magnet. And so what you can see here is the winding of the coil for the Brookhaven magnet. And what this really is, the Brookhaven magnet is one piece of superconducting wire that goes all the way around the ring, goes through, goes all the way around the back of the ring, comes out, goes all the way around the front of the ring. So it's one continuous piece of superconductor, which essentially gives you a perfect magnetic field. And then you get non-uniformities once you try to shape that field, but you're really starting out with an ideal magnetic field doing your experiment. So the first decision we had to make with the Fermilab experiment was to reuse the Brookhaven magnet if we could. And the other question was, you know, should we do this at Brookhaven or should we do this at Fermilab? And Fermilab turned out to be the right place at the right time. And this is, you could see this in this picture. If you look at Fermilab, this is what it looked like before 1985, before we started making antiprotons, where we had a LINAC and a booster and the main ring and a couple of rings in that. That was pretty much all we had. Now, today, what we have is a much more diverse complex. So we have the main injector here, we have the antiproton production facility, and once Tevatron Run 2 ended, these were all available for muon physics, because even in making as many neutrinos as we possibly can, we still dump a whole bunch of protons into the beam dump while we're ramping up the beams to make high energy neutrino beams. So we just have tons of protons left over, and we've got all these different rings that we can use to manipulate beam. And as it turns out, we can do the entire Brookhaven data set about every 4 to 6 weeks of taking data. And so that was the clincher. Once we had the ability to really make large factors of improvement in the statistics over Brookhaven, we decided that we'd just have to move the Brookhaven ring to Fermilab and do the experiment here. So now it wasn't as easy as we thought. We had to move it from New York to Illinois the hard way. This was the first group of people that went out to Brookhaven in the summer of 2011. You can see here, this is actually a U-Haul truck. So the first summer we worked on this project, the only thing we had money for was a U-Haul, right? So that's what we had and that's what we got. And then eventually within a couple of years, we got the few $1 million that it would take to move the ring. And so we moved the ring by barge around the US coast up the Mississippi River. Here you can see it going past the St. Louis Arch. We got it as close as we could to Fermilab by water, but then had to close down the interstates to get the ring to Fermilab from the water. And then once we got it to Fermilab, we had a big party and invited all our friends and neighbors to come and see the ring. And then this is when the ring is about halfway together in the building. We had a collaboration meeting, and this is one of our favorite collaboration pictures with everybody inside the ring. So one of the first things we have to do when we're putting the magnet together, we call shimming the magnet. So a cross section of the magnet looks like this. We have a couple of pole pieces. We've got a north and south pole. And then we've got an iron return or a steel return, which is in a C configuration. So this is a C-shaped magnet. And the reason we do that is because the muons decay to positrons and the positrons come out this way, and we have to detect the positrons. So we need some detectors here, and that's why we're going with a C-shaped magnet. Now, the first problem we have that is when we energize the magnet, it wants to open and close, okay? So when we build the magnet, we actually have to put these north and south poles at an angle, and it has to be exactly the right angle So when the magnet closes up again, the pole pieces are going to be parallel. Okay, the other thing we have to do is do fine tuning of the magnetic field. And one of the ways we do that is by limiting or varying the size of the air gap. So the magnetic strength here is, proportional to the air gap that you have between these pole pieces and between the steel here. And so we have wedge shims, what we call wedge shims, that we move in and out by turning screws. And, you go in there and you turn a screw by a quarter of a screw, and you move this out by, a handful of microns, and you're varying the magnetic field in the pole gap in this region by doing that. So, there's thousands of these around the ring, and it's, going around and iterating to, get the field to where you want it. We also have what we call rose shims or edge shims, which are just material that we add to the corners of the pole pieces here. And what that allows us to do is get rid of a lot of the higher order components in the fields, a lot of the sextupole and decapole components of the field, we can get out with those. And then finally, we have a set of surface coils that are active coils that we have all around the ring that we can run a current through and make essentially any type of configuration of magnetic field within our dynamic range to cancel things out. Now, that was the second final. The final thing that we had to do was that didn't quite get us to the dynamic range that we wanted. So we went around our vacuum chamber, and we had a very smart graduate student here figure out different configurations of material. And what we did was we sat down and we had an army of graduate and undergraduate and high school students cut up little pieces of iron and weigh the little pieces of iron. And then we made all these very nice configurations of iron and pasted them all the way around the magnet, both on the top and the bottom. And that kind of got us to the place where we could shim the magnet better than Brookhaven could do it. Okay, so I'm going to show you that here. So this blue here is the dipole field of the magnet going all the way around the ring from 0 to 360 degrees. This is the uniformity that Brookhaven got to. This was the uniformity we had at Fermilab when we first put the ring together before shimming. And, oh, I'm sorry. And you could see that play here. So what we're doing first is we're kind of tuning this shim package. We're calibrating it and figuring out how much things are going to change if we turn the wedge shims by a quarter of a screw, right? And then we're starting to put that into place. And now what you're going to start to see is where we started putting in these laminated foils. And you'll see it right away. So that's one of them. That's another one. This is, we're testing them to see what happens when we put them in. So now we've put all the foils in, and you can see blown up now that we're doing about a factor of 2, a little bit less than that, better than uniformity at Brookhaven. So that was our starting place. So that's a big part of this experiment, is just putting that magnet together and getting the magnet to be where it needs to be. Now we want to turn to putting muons in there and measuring the muon procession frequency. And for there, we take advantage of the V-A decay, which kind of pushes the positron into the direction of the spin. And the highest energy positrons, are always going to be aligned with the muon spin. So if we make a cut now on the high energy positrons, what we're going to see are regions like this, where the spin and the momentum are aligned. So if the positron is coming out along the spin direction, when the spin and momentum are aligned in the lab frame, this is going to give us the highest momentum positrons. And so if we make an energy cut there, we're going to have high efficiency when the momentum and spin are aligned. Now, if we come over here where the momentum and spin are 180 degrees out of phase, this is going to give us the lowest momentum positrons. And so if we make a cut, we're going to have low efficiency in that region. And so that's why what we're measuring here is then this frequency which is the difference frequency between the momentum vector and the spin vector. And that's really what we're doing. So what we would see now is if g-2 were equal to 0, exactly equal to 0, the spin and momentum would always stay aligned because the difference between these frequencies was g-2 over 2. And when we looked at our data, we would just see a flat lifetime, right? We'd see the muon lifetime of just the counting positrons versus time. But now if you have g-2 equals 0.002, this is what the data looks like. Okay, so you can just see this is popping out automatically. As soon as you take data for 5 minutes, you could say that g-2 is not 0. And another interesting thing about this is it shows that what we're actually measuring is we're only measuring the radiative corrections. We're only sensitive to the terms which are different from 2 for g. And that automatically gives us kind of a couple of orders of magnitude that we don't even have to worry about measuring. And that's another reason why we like the storage ring technique. So we measure the positrons from muon decay with calorimeters. We have the calorimeters in 24 regions around the ring. They're on sleds that look like this. And within the sleds, there's a 9x6 array of lead fluoride crystals. So we have 54 segments of crystal in here. And you can compare that to Brookhaven, where Brookhaven, it was just one monolithic calorimeter. And when we talk about systematics, you'll see how with Pileup being one of our main systematics, you know, this is a big win for the Fermilab experiment, having this segmentation. The other thing we have is we read out the calorimeters with 800 megasample per second waveform digitizers with 108 megabyte memory. And you can compare this again to Brookhaven, where they did about half the sampling rate, but with only a 64 kilobit memory. So we're allowed to write an enormous amount of data out of the experiment, which allows us to have lower thresholds, do many more systematic studies than they could do at Brookhaven. It also makes us drowning in data, which is a little bit of a problem, but you know, that's a problem that you want to have. And then the entire system is read out with a GPU-based data acquisition system, which can handle about 18 gigabits a second. And again, you can compare this to Brookhaven, where they were writing out about 1 megabyte per second. And the thing about Fermilab and Brookhaven is the rate, the instantaneous rate is the same between the two experiments. So the number of muons we have at the beginning of each fill is the same between Brookhaven and Fermilab. The difference at Fermilab is we fill it much more frequently than they did it at Brookhaven. And so that's how we get all the extra data. It's not that we're, you know, adding 10 times more muons in there. We're essentially doing the same experiment that they did at Brookhaven. We're just doing it more frequently, more times a second. Okay, so now that we've stored muons, the next thing that we have to understand is beam dynamics. And this is the plot I showed before, what we called the wiggle plot. And what I tried to explain is what this actually is that we're looking at is an efficiency function, right? So that scares most experimentalists when you think about having to know your efficiency function down to that level. And one of the biggest things that can change that efficiency is where the muons are in the storage ring. Is the muon close to the calorimeter when it decays? Is the muon far away from the calorimeter when it decays? So beam dynamics are a huge issue here. So what we could do is we could look at this data and we could fit it with just the 5-parameter fit, a cosine omega t plus a phase, and we could look at the residuals and then look at the power spectrum to those residuals. And what we see is these enormous residuals. You can't see these by eye, but once you do the FFT, you know, these are popping out all over the place. And what these are different frequencies associated with beam motion. So this is the horizontal motion of the beam. This is what we call swimming of the beam. This is the horizontal width modulation, which we call breathing of the beam. These are the same thing for the vertical width and the vertical mean oscillation. And you could see these things even beat off of the g-2 frequency. Okay, so we have to understand these very well in our fit. These are the things I just said. We also have to know where the muons are so we can say which magnetic field we should be using. And we have to measure all these beam parameters in different locations as a function of time so that we can get these into the fit and take these out of our efficiency function. So we do these with tracking detectors, and what we have is tracking detectors in front of 2 calorimeters. And these are doublet layers of 5mm diameter straws, 15 micron wall thickness straws with UV separation, UV about 7.5 degrees stereo angle. And they're located at 2 places, about 90 degrees and 270 degrees. And we have about 125 micron hit resolution, which when we extrapolate this back to the beam position comes out to be about sub-millimeter resolution in the beam, which is what we need. And what you could see here, this is with data, this isn't with simulation. This is looking at the beam, and what you can see is the swimming of the beam going back and forth. You can kind of see the breathing of it getting wider and wider. It's a little hard to see the vertical motion because it's a lot smaller, but it's there. And we measure all this with the tracker. So once we measure all these things, we can remove them essentially by putting them into the fit. So instead of looking at a 5-parameter fit of just, a cosine omega t plus a phase with an amplitude and a lifetime, we wind up with a 22-parameter fit where we're looking at the vertical motion, the horizontal motion, everything has to go in there. And when we put all those components into the fit, you can see this is the residuals before we put them in. Here's the residuals after we put them in. So we've included all of these things. We also have to include lost muons, but I won't talk about that right now. But you could see it's fairly significant how much the beam is moving in the horizontal and in the vertical region. And so once we put all those in there, we can do the fit. And we're not floating these when we do the fit. We're all measuring these with the tracker and then putting it into the calorimeter data fit. And at the same time, we could derive all these from first principles with multiple beam dynamics Monte Carlos, and we have good agreement between what we'd expect to see and what we're finally getting. Okay, so now we can turn to trying to understand systematic uncertainties. So as we said a few times, this is our wiggle plot, and the dominant feature is this cosine omega t plus this phase. And what this phase is, it's the phase between the spin and the momentum at the beginning of the fit. So at this point. So you inject muons. That muon distribution has a momentum spread, and it has a finite polarization. So it has a polarization spread. And you have the mean value of the momentum and the mean value of the polarization. And this phase is the difference between those 2 mean values at this point when you start your fit. So we can think about the systematics. They all come from if we have any time dependence in this phase distribution. So if you just think about that as a Taylor expansion, if you take this phi distribution, you could break it up into parts that are independent of time and parts that are dependent on time. And when you do your cosine omega t plus phase fit, any time dependence in this phase is automatically going to get pulled into this omega term, all right? And so what we like to say is that things that change early to late in the fill typically lead to a time dependence in this phase. And that time dependence in phase directly biases the extracted value of the muon procession frequency. So we could look at some examples of that. The first is Pileup. So what we expect to see in our detector, we're looking for high energy positrons. So if we see a positron that's above our threshold, it's a high energy positron, it means it had to come from far away from the detector. This decay point could have been like 2 to 3 meters away from the calorimeter, okay? And you have a high energy positron comes out and it comes in and it hits the calorimeter. And at this point, you have a phase advance between the momentum and the spin, which I'm calling phi 1, right? Now, pileup is what happens when we have two low energy positrons simultaneously coming from two muon decays in the same region and going in the same direction and landing very close to each other in the calorimeter, so that these two low energy positrons get reconstructed as a high energy positron. Now, at this point, there's a very different phase difference between where the muon and the spin is. So, and the other issue is that we're storing muons for about 10 lifetimes. So the probability that you're going to have multiple muons decaying at the same time is going to happen in the first couple of lifetimes. It's not going to happen after 8 to 10 lifetimes. So this is an effect that happens early in the fill, where you're seeing an ensemble of two different phases. And then late in the fill, you'd only see this phase here, okay? And the difference of those would directly bias omega. The other thing that we have to worry about a lot is gain changes. So as I mentioned, we're looking at these over 10 lifetimes. So the rate of particles that are coming into our readout electronics are very, very different in the first lifetime than compared to the 10 lifetime. And if you have any saturation effects, the saturation effects are going to effectively shift your threshold, okay? So early, you might have effectively a higher threshold, which is going to push the positrons that you accept back a little further. And late, when you're not saturated, you can have a lower threshold, and you're seeing positrons over here. So these are two examples that we get, and they're two of the main things that were driving systematics at Brookhaven, and some of the main things we had to get rid of in the Fermilab experiment. So, and the other thing to remember for this is that the design of the experiment never really is driven by absolute performance, but it's driven by relative stability early to late. We're always trying to get that early to late stability. So one of the main ways that we've dealt with these two systematics is with a beautiful laser system that was in-kind contribution from our Italian institutions. And it's a highly tunable, very precise laser that sends pulses to all our crystals. And it can send pulse trains, it can send different separation pulses, it can send them during the time that we're taking muon data, it could send them between data fills. And what we can work out to very high precision are things like the gain sag. So when we inject muons, we do have a flash, and that reduces our gain a little bit. So, we have to determine what that is. And this is the gain function for that. And you could see, it's not a big function here. We start taking data around here. So, we're not really worried about this, but we have to measure it very well. The other thing that we have to worry about is the recovery between two consecutive hits. So we have silicon photomultipliers that we're using to, which is basically a pixelated detector. So when a positron comes in and hits that crystal, it knocks out a handful of pixels, and those pixels have a recovery time. And so the next positron comes in, and you're not necessarily dead because you didn't hit all the pixels the first time, but you don't have as many pixels, so you have a slightly lower efficiency. And here's the effect of that you can see. And this is, again, because we have this laser system, we could work this all out. And so what we make is templates for every different configuration that you can have, and for every different crystal. And you could see this is what a hit looks like when we have one positron at a time. This is what a pileup hit looks like. And you can see we have a lot of fidelity here. And what it's allowed us to do is take the pileup and gain systematics and reduce these from about 180 part per billion at the Brookhaven experiment to a 41 part per billion error at the Fermilab experiment. So we still have residual systematics from beam motion that we have to worry about. And to understand those, you need to know a little bit about how we store beam. So when we inject beam, we put it in our ring, and we have 4 sets of electrostatic quadrupoles around the ring. And these provide the weak focusing that keep the muons stored and keep the muons from just drifting out of the plane of motion. And we had a problem at the end of our first run where we have two different types of high voltage feed through resistors that we use to get the current on these plate. And this type of resistor here, where you could see it's kind of a bunch of resistors soldered together, we had arcing across these solder joints here, and it damaged the resistors. It didn't break them, but it changed the resistance. And so it changed the RC constant of the quadrupoles. And what you could see is this black line here is what the quadrupoles are supposed to be doing. We have to pulse them each time the beam comes in because we can't keep them turned on all the time. So what's supposed to happen is we're supposed to turn on the quadrupoles. They have this RC constant here. The beam gets injected here at this black line. And then here's when we start taking data. Okay, so everything's nice and flat there. The other thing that's going on is on half the quadrupole plates, we're scraping the beam, right? So we want to take the beam, the initial beam, and move it on to Calorimeters so that we could scrape off any muons that we would potentially be losing during the fill. So that's what's going here. So we one set of plates we turn on, the other set of plates we turn to 1 voltage to scrape the beam, and then we bring up to the other volts to the nominal voltage to store the beam. Now, once we broke these resistors, and it was 2 resistors that were broken out of 32 resistors, but what happened then is this is what our quadrupoles looked like. Okay, for the one that was supposed to come to flat top, you know, it was taking forever to come to flat top. For the one that was supposed to be scraping, it wasn't doing a good job scraping. It was also taking forever to come to flat top. And if you look at the beam then, this is the beam trying to get to the center of the ring in the early data sets that we had. And this is the beam in the data sets where we had the broken resistors. So you could see we just have, it's, you know, we try and get away with, well, we can't get away, but we can kind of include the differences here. But here, you know, it's just a really big problem. And, you know, we had to throw away a fraction of this data just by starting out later time. But we also have these residual systematics that we have to understand with. And again, we just have to think about this. The problem is that the beam is moving early too late, which is the thing that kills you. And so now we have to understand does that change the phase? Is that making the phase change early to late? And unfortunately it does, because there's a coupling between the phase and the acceptance. And the way to understand that is if you think about muons that decay when the spin is pointing outwards. So there's a divergence in the positron beam. And if the positrons have a large path length to get to the calorimeter, by the time they get there, the spot size is going to be pretty big. Now, if the muon decays pointing in towards the calorimeter and you have the same divergence in the beam, when it gets to the calorimeter, the size of the beam is not going to be as large. So if we had infinite acceptance in our calorimeters, this wouldn't be a problem at all. But we have finite acceptance, and so this finite acceptance is leading to a problem. And now that still wouldn't be a problem, except for the fact that, you know, in general, when muons are pointing into the ring, they're at 90 degrees out of phase from when muons are pointing out of the ring. So these two different effects here are happening at different points in the phase map of the muon. And if you look at the calorimeter face, this is where the positrons, or where the muons decayed, and what the phase advance is once it hit the calorimeter, depending on where it decayed in the vertical position and the horizontal position. And you could see it's, you know, it's not a huge effect, but it's definitely an effect. And this also wouldn't be a problem, but it's a problem because the beam position is changing early to late. Okay, so if the beam was always in the same place, you wouldn't care. But since the beam position is changing, you have to worry about that. Okay, and you could see that here. This is, these black lines here are just, you know, the projections from the phase map here. Here's where the phase is along the vertical component. Here's where the phase is along the horizontal component. And here's where the beam is. The red is where the beam is early in the fill. and the blue is where the beam is late in the fill, okay? So we're seeing this phase difference, but since we know what this phase difference is, we can measure where the beam is, and it's fairly straightforward to calculate this phase advance using simulation. So we can come up with the correction for this. And for that final run period, which was our worst run period, the correction is about 164 part per billion with an 80 part per billion effect. So this is the type of thing we don't want to do. We don't want to have to make these corrections, but at the end of the day, if we have any effects early to late, we have to make these corrections. So here's the results from the muon procession frequency. What you see here is an army of a small army of graduate students, 5 or 6 of them, have all measured this data, and these different points here or these different bins are different analyzers and different analysis techniques. And then the different colors are the 4 run periods that we have. And so we have very good agreement between the different analyzers and between the different run periods. We also look at things. This is the procession frequency blinded. Okay, so this number doesn't mean anything here, but this is varying the start time in the fill. So you start at 30 microseconds and ask what your result is. Then you start at 40 microseconds and ask what your result is. And these bands here are how you would expect things to vary based on systematic and statistical errors. And what you could see is very good agreement. And this is telling us that, there's no big issues that are coming in early to late that we've missed. Okay, and we do that with all our parameters. The main one is, of course, the omega A. Now, that's not the end of the story. We do have a very exhaustive list of systematics. We have other corrections. And what we end up with at the end of the day is a statistical precision of about 434 part per billion and a systematic error of about 556 part per billion. And then we're making corrections. We have to make corrections to it, and they're run dependent. And they range between about 449 and 601 part per billion. Okay, so that's half of the story, is the muon procession frequency. The other half is measuring the B field now. And I've been talking for about an hour, so I'm going to go very quickly through the magnetic field part. But if anybody has any questions afterwards, please ask me. Okay, so we measure the magnetic field using nuclear magnetic resonance. We have several components of that. So we have a spherical calibration probe that we use. We have an MRI magnet, which we use to cross-calibrate everything. Here's some more about the different calibration. We have a trolley that goes around the ring and maps out the field at different locations. And you could see here how the field is varying around the ring. And then we have to, we can't, of course, take trolley runs when we have muons in the ring. So what we have is NMR probes that are embedded in the beam pipe in the vacuum chamber. And what that allows us to do is track the magnetic field between trolley runs. So we have a trolley run here, we have a trolley run here, and this is how the field is changing between those trolley runs. We don't get perfect closure. That is something we understand. It's a weird temperature dependence that folds into it, but that basically defines our systematic error there. Now, this brings us, though, to kind of our second leading systematic and our leading systematic from the field measurement. And this is what our beam structure looks like. So we have muon fills are about 1 millisecond long, and we fill the ring every 10 milliseconds for 8 pulses. And then we have a long gap, and then we fill it with another 8 pulses. Now, when we measure the field using NMR, this is much slower. This is something that happens over seconds, and it's something that we only do every few seconds, okay? And it's asynchronous to beam delivery. So there's a built-in assumption that nothing is changing faster than the NMR can see it. NMR is pretty slow, all right? And also that there's nothing correlated with the beam, so that the protons in the NMR are saying the same beam that the muons are seeing. So we proved this wasn't anything with the electronics, but we are having problems if we get back to our quadrupoles. So we upgraded our NMR system so that we could synchronize it with beam delivery, and this is what we saw. In regions without the electrostatic quadrupoles, we have a nice flat beam or a nice flat B field. And in regions with the quadrupoles, we're seeing this huge ringing every time beam shows up. And what that's coming from is mechanical vibrations in the quadrupoles. So you have a conductor in a magnetic field and you pulse a bunch of charge into it and a bunch of current into it, and that gives it an impulse. And that impulse starts to make it vibrate mechanically. And you can see here, this is the, there's a natural resonance about 50 hertz. Luckily, we're up here at about 100 hertz. We're a little bit worse than they were at Brookhaven. If we were at 50 hertz, we would have been dead. But this is something we have to take care of. So we measured this very well. We had to build new probes to work in the quadrupole region. And you could see here, this is the ringing that's happening. And these gray lines here are our bunch train when we're sending beam into it. So what we have to do is measure that very well. And then we have to say what the magnetic field is and how it's changing during our measurement. And we have to make a correction for that. And we got lucky with this. When you look at it, you could think about it when you get back to these nodes, right? There's places where the fields are going to naturally cancel out just because of the different types of vibrations that are happening. And when you look at it around the ring, it kind of cancels out and you wind up with about a 15 part per billion correction with about an 82 part per billion uncertainty. So this is one of our dominant uncertainties, just because we have to map this out better, right? And it's how well we could really prove that things are canceling out. And we have that for future runs, but for this first data set, this is just winding up being our dominant thing. So this is what we get then for our proton procession frequency. We have an uncertainty of about 114 part per billion. These are all the systematics associated with that. And when we put it all together, we have these two frequencies, the muon procession frequency and the proton procession frequency. And they're allowed to change, but G-2 is their ratio. So the thing that's supposed to be constant is something lying along this line. These are our 4 different data sets. It's not great agreement, but it's good enough agreement. The chi-squared probability is about 7.8%. That's the type of thing where at that level of agreement, you could either spend 5 years trying to understand if it's a statistical fluctuation, or you could just put it out and keep taking data. So we're putting it out and taking data. And so what this winds up then, we have a Fermilab result for G-2, and it confirms the Brookhaven result for G-2. So if we get back to our assumptions, this doesn't look like it's new physics. It doesn't look like it's a problem with the theory, but now it doesn't look like it's a problem with the Brookhaven experiment either. So we have this discrepancy now, the update from the theory initiative. We have a combined value from Brookhaven and Fermilab, and the mystery remains. Moving forward, we expect 2 more rounds of publication. So this is our current error. We expect our final error to be around here. A lot of the systematics that we have associated to motion, we have better handles on now. They can't be completely removed, but they can be better measured. The other thing to mention is that there is a J-Park Muon G-2 experiment under construction with very different systematics. So for people who look at this and say, well, maybe there's some hidden correlated systematics because you're using the same ring, the J-Park experiment will put that to rest as well. So to conclude, we've not found any new physics that can explain the Muon G-2 discrepancy. We continue to search. We have not found any problems with the standard model calculation that could fundamentally solve the discrepancy, but more data and more lattice calculations are on the way. We have found we've not found any problems with the Brookhaven result, and it's confirmed by the new Fermilab result. And we've got a lot more data coming in, and we expect data from J-Park. Now, any of the above could solve this mystery. We could either discover new physics in the next LHC run. We could determine that the QCD error is underestimated, or as we add more data to the G-2 result, it could drift closer to the standard model. But for this point, the mystery remains. Thank you.
Thank you, Brennan. So now for the questions. So let me see if there is people with. Oh, there is a question here. Gustavo, please.
Hi. So first of all, Brendan, thanks for your great presentation, and also congratulations for the result and for all the work. I mean, this must be a great feeling to be at the end of this great run of generations of people and do such a great work getting this result to be so precise and so well realized. So it's really a great achievement. So congratulations.
Thank you.
But so I'm a theorist. So my question, I'm always in awe on the work of experimentalists, and so, but I really don't have any specific questions for the experiment. My problem is this. So let's assume for a second that this first lattice result. I mean, I've been hearing about this since I was a graduate student, which of course, obviously, is a long time ago. Particularly the hadronic contributions being a problem, and the theory wall for the G-2 experiments, etc. And now we finally, after all these decades, we have a theoretical lattice result. Let's call it the lattice result, because it's kind of experimental, theoretical, experimental. And now, so the question is, as you well put it, there is now a problem between, if it's correct, I mean, the lattice results converge around the BMW result. Now the question is, why is it that there is disagreement with the extraction from E plus E minus, which we always assume to be so well grounded, right?
Right.
And so the question is, you mentioned this huge collaboration of almost 200 theorists that have been working for a long time. Is there any hint from them of how can you bring these two together? Because I see the experimental side going very well in the direction of making a very precise measurement in the future yourself, and then eventually J-Park. But I don't know if the theories are going to be able to match, I should probably include myself, to match this precision in the future. Is there any hint that there isn't anything wrong, for example, with the or there could be anything wrong with the extraction from E plus E minus? Any theoretical assumptions we're making there that could be wrong, like neglecting interferences between different channels, or maybe continuum contributions? I mean, you always measure n particle final states, but maybe there is a continuum contribution in the dispersion relation. Is there any hint that people are talking about to bridge this gap between the two theory calculations?
So I think one, so people focus on two things, right? So right now you have the difference between, if you just think of the E plus E minus, you have the Babar and Chloe difference, right? And the fact that they don't agree means there's something somewhere, right? It's not a statistical fluctuation between those two. So something is happening, and the Babar is at 10 GeV radiative return. The Chloe is at much lower energy, right? So you have two radiative return experiments, which are dominating things now, and they're at very different energies, and they're not really giving compatible results. So I'm not an expert on this, right? But I always worry that there's something wrong with the radiative return, that you're doing that. So what I'm looking forward to is the new Novosibirsk data, which is going to be direct R-scan data. And it's going to have, you know, the statistical precision equal to Chloe and Babar. So on the experimental side, that's something I'm really looking forward to. On the Lattice side, I like to think of it in terms of, you know, the example I like to think of is, you probably know the plot that I'm thinking of, that Andreas Kronfeld shows a lot, which has kind of all the pseudo-scalar masses, and it shows the experimental value and the lattice prediction, and the lattice stuff is all over the place. And then they kind of realized there was one more thing missing on the lattice, and when they put that in there, you know, everything lined up, right? So I think we have to, you know, have a certain amount of patience with the lattice people, right? They really have one calculation now, which is at high precision, but they have multiple groups on it. So I expect, as multiple groups are reaching that precision, you know, as a community, they're going to find things, and their numbers are likely going to move around a little bit, right? So I think the most likely value is that their number is going to settle on the E plus E minus value. Now, the good thing though is what I always wanted is you want all these experiments so that, you know, when you look at this distribution of values, you know, are we looking at a Gaussian distribution, or are we looking at a flat distribution, right? That everybody that predicts this is just going to be another 1% away from all the other predictions. So, you know, the other thing I like to think is that, okay, what's the worst case scenario? The worst case scenario is we look at all these measurements and we have an idea ourselves of what the real error is, right? Right now, the error that we use is a combination of what everybody claims their error is, right? And if you have enough different determinations, then the error just becomes the spread in those determinations. So the worst case scenario is, you know, we kind of know what the real error is, right? And it may turn out that it's just a lot bigger. And that's, you know, with it's not different from electron G-2, where the experiment is, you know, much, much better than the theory, but, you know, you do the experiment, eventually the theory will catch up, right?
All right. Okay. Thank you. And thanks again for your presentation. That's great. Thank you.
So we have another question from Alexei Petrov. Please, Alexei.
Yes, hi. It's a little bit of a comment. Hi, Gustavo. Nice to see you.
I knew I was provoking you. That's part of my question, was to provoke you. But
very good. Very good.
That's a private thing.
Right. So one of the comments is that it is true there is a difference between Chloe and Babar data, but the important comment on that is that it does not explain the discrepancy, right? Yeah. So it does not explain the discrepancy between the experiment and the theory. The second comment is on BMW. I mean, indeed, within a year, as far as I know, there would be several calculations, lattice calculations done with the same precision as BMW. However, in the average that actually Brendan showed, there was a approach that both included data and lattice, right? It was totally consistent with the plus and minus result. And the third comment is actually also related to BMW, right? I mean, if you look at their prediction, you know, as a prediction, it does not only affect G-2, it also affects, for instance, alpha S determinations at the Z pole, right? So basically, it affects in some way, precision electroweak data that, you know, they explain it in such a way that, you know, some of the data, you know, main discrepancy comes from like a raw region, but nevertheless, there is their prediction would affect electroweak precision data as well. So yeah, this RBC UKQCD, that little thing over there. So it's a combination of data and the lattice results. Thank you.
Yeah, so it's right. the most you could do is move the problem somewhere else.
Questions? More questions? Oh, no, I don't see. Oh, there is one, sorry. Where is the, Karsten Hansen, please. You can, Karsten, you can ask your question.
Thank you. Thank you, Brandon, for this very nice presentation. That was very impressive, and congratulations on those new results. I have a more operational question. I mean, this is a very good example with all the LHC experiments. We are kind of tuned into this fact that collaborations always have to be big to operate successful experiments. But seeing from your pictures, your collaboration is rather small. So what does it take to can you describe the actual data taking period and how many people are involved in this?
Yeah, so
and then, sorry, this feeds into this is a two-parter, sorry, into the next question. On one slide, you mentioned this, there's, I think it was on the mapping of the resonances of the quadrupole, I think, that you did this during the COVID shutdown. So how were you affected by the COVID crisis?
Yeah, so this is, like how many people we have. We're kind of keenly aware of that right now because, we have a 200-person collaboration, and when we're taking data, usually about 100 people are here and are coming in and out. So in this run period that we're taking now, we have 27 people. Because that's just who we have, who lives here, right? Nobody can travel, and it's been a nightmare, trying to run with 27, and because we run 24/7 and 7 days a week, and we're doing it with 27 people, but I think if we had 26, we'd fall apart. But so it is a lot smaller. The thing that is actually the most different, which I alluded to, was the data that we have. So we have data sets that are kind of multi-petabyte a year, which are still small compared to the LHC, but they completely wipe out our experiment, right? We're drowning in data. And we have, and if you think of a collider experiment or most experiments, as a collaboration, you process the data, and then as an analyzer, you pull out a chunk of this data. And depending on what you're looking at, your data might sit on your laptop, and you run over it, as many times as you want. You run over it a couple of hundred times in a year, right, before you put a result out. So for G-2, every analyzer looks at every single event that we take. And an analyzer wants to start at the raw data, right? And wants to do their own reconstruction and their own thing. So it's like as if every single analyzer needs their own tier 2 or tier 0, right? And because the way we look at the data is so different from other high energy physics experiments, we're constantly breaking Fermilab, right? We're taking down the Fermilab computer farm all the time, because even though, we're much smaller than an LHC experiment, we're doing something in such a different way than other experiments do. So in terms of, keeping the experiment working, it's not that different, right? It's not that different from D0, or the LHC. Things are breaking, you're going in and you're fixing them. But what's really different for us is just this enormous amount of data that we're just drowning in. Oh, and and then so what we do is, we're taking muon data about 9 months out of the year, and then we have a 3-month shutdown. And in that shutdown, we have a an enormous list of things we have to fix. And we also have a list of magnetic field studies that we want to do. And we usually say, okay, we're going to spend a week doing those magnetic field studies. And then we're going to, rip the experiment apart and fix everything that's broken. So what COVID did for us, when COVID hit, I was able to convince people that we should keep our magnet on, right? That was the first battle, right? And then once we could convince people that we could keep our magnet on, then we let the field team go in there like one person at a time, right? We never had more than one person in a room at a time, and make measurements. And instead of trying to make these measurements in 1 week, we made them over 6 months. And there were 2 of these measurements where actually we had spent more than a year trying to figure out how to make those measurements. And then, that time period that we got in COVID, we actually were able to dedicate the time to do it. And those were the couple of the final things that we had to do before we got the publication out. So that's our good COVID story, right? That it kind of gave us the time to make those measurements. And if we ever would have said, I need 6 months to turn the muons off and do nothing but field studies, we say we're going to do that at the end of the run, right? We're going to take field studies for a year after, once mu to E starts running. But that allowed us to do it here, and that made a huge difference. It really basically allowed us to get the publication out this time.
Thank you. Once again, congratulations to everyone involved. That's pretty cool.
Any more questions? I don't see any. So thank you so much for your talk, and congratulations once more for this beautiful experiment and the first results. I just have a last question about when do we expect next results from you guys? Next year?
Well, my number is 2 years.
2 years.
And
okay.
Other people will give you the number of 1 year.
Yeah. Why 2 years?
Well, so it's about a year to get things out. And then, if you say, okay, well, there's probably going to be at least a year worth of stuff that we didn't anticipate, that puts you in 2 years. Right?
Okay, so, I see.
So I expect, if we're very lucky, and we don't find any new problems with the new data, we could get something out in a year. But we're moving into a new statistical regime.
I see.
So we expect that we will find new things, and it's hard to predict how long it's going to take you to understand those, right?
Yeah.
So we know how to fix all the things that we already fixed. Right.
Okay, so but you might have some other things that you don't expect to have to fix next time. I see.
Or the way I say it is, we will have things.
Okay. So thank you so much, Brendan. It was a pleasure to have you, and it was really, really a beautiful experiment. Thank you.
Okay, thank you very much.
Bye bye.
Everybody.